Okay, so now let's dive into 37, arrayMaxConsecutiveSum. And what this one is asking us is, if we're given an array of integers, we want to find the maximum possible sum of some of its k consecutive elements. Okay, so let's break this down first of all. I want to start at the end here. So k consecutive elements. Well, k is just a number that they're going to be giving us. So maybe it's 2, maybe it's something else. It could be anything between 1 up to and including the length of the array. So it could be equal to the length of the array, and that's probably worth keeping in mind. That may be something we need to keep in mind. Anyway, all right, consecutive elements. Well, basically we mean things from the array that are all right next to each other. So like 2, 3, and 5, or like 5 and 1. I guess that I really should only be using 2 of them because k is equal to 2 in this case. So when we're saying k is equal to 2, basically what we mean is either it's 2 and 3, it's 3 and 5, it's 5 and 1, or it's 1 and 6. And we want to find the maximal possible sum. So when we say the sum, we mean add those numbers up and see which one is the biggest. So 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 1 is 6, 1 plus 6 is 7. So 8 is the biggest one here, and that's what we want to return as our answer. Okay, so that's basically going to be our plan for this one. So let's do that. So we'll start by doing something like this. We'll say let max be assigned the value of 0, and ultimately max is the thing that we want to be returning. And then from there, we're going to go through a loop. And we're basically just going to loop through input array. So we want to make sure that this is going to be less than input array dot length. Be sure to not forget the dot length on the end of that. And in terms of what this is doing, it's going to sort of reassign max. So we'll have like a sum in here, which will start at 0. We'll do some stuff. And then after we do that, we'll say something like max is going to be math.max, max sum. So basically what this is saying, actually, here, I'll rewrite that another way. It's basically saying if sum is greater than max, then max is assigned the value of sum. All right, so these two things are equivalent. This one here, this one here. I'm kind of now realizing it looks like this one down here is actually a bit shorter. So, I wonder which is better. I mean, this one is like, it's calling math.max regardless. This one is basically saying, well, do we need to reassign max? And then it's only reassigning it if it needs to. So maybe we'll keep that one actually. Maybe that's better. Anyway, the point is, before I get into like what kind of stuff we're going to do here, which is basically just finding the sum, I just want to talk about the way this whole thing is structured before we go any further. So we've got max, it starts out as 0, and then we're going to find out all these other sums. Right now there's 0, but eventually there'll be other things. And then we basically want to say, well, if that sum you just found is greater than what max already was, we'll say max is going to be that sum, and then we're going to return max at the end. So the thing is, what if we had like all negative numbers in the array? What if the array was just a whole bunch of negative numbers? Well, then the maximum sum you'd be able to get would have to be something negative. So 0 would actually be misleading in that case. 0 would be too big, and so it would actually throw off our results. So that would be a problem if our input array had a bunch of negative elements in it. So let's actually take a look at our constraints, and what we find is, no, actually the elements inside input array, not only are they not going to be negative, they have to be positive. So they couldn't be 0 either. So they go from between 1 and 1,000. So it's totally fine for max to be equal to 0, because max at the very least would have to be equal to k. Why k? Well, because k is the number of elements that are going to be in the consecutive subsequence or subset here, subarray. So k is the number of elements. Each of those elements is at least 1. So if there are 2 of those elements and each of them have to be at least 1, then our sum there is going to be at least 2. So we could get away with actually saying max is assigned the value of k. It's a little more bold. That's kind of a bold move, but I like it. Okay, so we'll do that. Let me know if anyone has any questions about why we can use k here instead of 0, and why we don't have to do something like a negative a billion or like negative infinity or something like that. Okay. So let's continue with this. We're going to do some stuff. So specifically, what are we going to do here? We're going to get the sum of the k consecutive elements beginning at I. That's the idea. Okay, so we want to find the sum of the k consecutive elements beginning at I. Okay, so I'm going to do something like this. I'm going to say let slice be assigned the value of input array dot slice, and it's going to go from index I to index I plus k. Is that going to work? Let's find out. So let's just do a quick console log of slice. This should go through the array and find all the slices we're looking for. So notice for the first one, we're getting the 2 and the 3. Great. We're getting the 3 and the 5. Great. We're getting the 5 and the 1. Great. We're getting the 1 and the 6. Great. Then we're just getting 6 on its own, and we're starting to think, that's a little weird. Why 6 on its own? Well, it's because this is going too far. So it's going all the way to input array.length, but really, I mean, if we need k elements, we can probably subtract a k out of that one. Let's see if that's going to work a little better. We'll see what kinds of slices we come up with if we're going only up to input array.length minus k. Well, now this is good. We're not getting the 6 on its own, but we're also not getting the 1 plus 6. So the issue here is it needs to be able to include this value. I could have put a plus 1 on the end, or I could just put the equals. It's one fewer character to do it this way, so that works for me. So those are the subsets we're getting in this case. For this one, we're also looking for 2 elements, and yeah, it could be 2 and 4, it could be 4 and 10, it could be 10 and 1, so that's good as well. This next one, we're looking for 3, good, 1, 3, 2, 3, 2, 4. This looks like it's working. This one we're just taking one at a time, and it's getting all of them, so good. Yeah, that looks good. We're getting the right slices out of that. So, okay. What do we want to do from here? Well, sum is going to be equal to, basically, it's whatever's inside the slice. Keep in mind the slice is like each of these are arrays, right? So we want to be taking everything inside the slice and then just adding it all up, finding the sum. So we'll just do slice dot reduce, and for a reduce we want a function that's going to take 2 inputs and return the sum of them. And as we've seen before, this is a really common tool for when you want to add up all the elements in an array. Now let me know if you have any questions about how this is working. I realize this might seem a little strange. If you're not used to arrow functions or a lot of ES6 kind of stuff, this should probably look especially weird, but let me know if you have any questions, we can talk about it. And what I'm now realizing is we actually don't need for sum to begin at 0, so I guess I'll just get rid of that and I'll put the let right here. Okay, so is this going to work? Let's find out. I'm curious about this one. And there we go. Okay, so that's passing all the visible tests. Let's submit that and we'll see if it passes the hidden test as well. And in the meantime, let's see. Oh, look at this. Okay, so this is pretty exciting. It's saying execution time limit exceeded on test 7. It got pretty close to the end there. It passed all 4 of the sample tests. It passed 2 out of the 3 hidden tests, but then it had an issue on that last one. So let's take a look at why that would be. Well, if you think about it, our array could be as many as 10 to the power 5 elements. What's 10 to the power 5? Oh, just 100,000. So it could be a really long array is one of the issues. And then the other thing is k could be as big as the array itself. It could be as small as 1, right? So we're going to have to go through a lot of these like slices, a lot of these reduces. This is a lot of stuff to be doing 100,000 times. All right, so probably this isn't the best way to do it. But oh well, we tried. We have information now. I don't want you to look at this and think, oh, well, that was a total failure, back to square one. Well, no, we're not on square one anymore. We're on square 2. We know what didn't work. So we have more information than we started with. It was a success. The experiment was a total success. It gave us information. Now, let's use that information and we'll try to do something, I guess, a little bit different. So, what's going to be different about the way we're going to attempt this one? Well, the main thing is that let's look at an example. So I'm going to go over to the whiteboard. Oh, there's already stuff on the whiteboard. All right, let's clear that. Sorry about that. Forgot to clear it ahead of time. But oh well. So let's say we've got our array, and maybe it's like 2, 5, 9, 1, 17. Okay, so we've got that, and we'll say in this case k is going to be equal to 3. And this is our input array over here, which is a long word, so I'm not going to write it out. But what I want to point out is basically if k is 3, we're looking at 3 possible subsets here. We've got 2, 5, 9. That's our first subset, right? And what was the sum on that one? So sum would be equal to 2 plus 5, which is 7, plus 9, which would be 16. Okay, so we got a sum of 16 for that one. And then the next one is 5, 9, 1. Okay, great. So then if I want the sum of that one, we'll add up all those numbers. So 5 plus 9 would be 14, plus 1 is 15. Cool. So then we'll look at the last one, and it's going to be 9. 1, 17. Okay, we've got our 3 possible arrays here, and then we calculate the sum on this one, and we'll add them up again. So 9 plus 1 is 10, plus 17 is 27, which means that this one's the winner, so that's good. But there's something I want to point out about what we're doing here. We've got these 3 arrays, and it's probably worth noting that they sort of have some elements in common. And like the larger k is, the more elements these things are going to have in common. Okay, now why am I pointing that out? Well, basically it's because what I'm trying to say is we don't need to do our sum every single time. You know, we don't need to recalculate the sum every single time. Like I did 2 plus 5 plus 9, that gave me 16. Then I did 5 plus 9 plus 1, that's 15. Then 9 plus 1 plus 17, that's 27. The thing is, when we go from this sum, so from the 16 to the 15 over here, what are we doing? Well, we're taking away the 2, the leftmost element, and we're adding on a 1. Right? We're just taking the next element. So it's kind of like we're just getting rid of the last element or the leftmost element and then adding on the rightmost element. So basically subtract 2, add 1. So if we take 16, subtract 2, we get 14, add 1, we get 15. So that's a much easier way to get to the next one. We'll just say minus 2 plus 1. And then from here to this next one, we'll say minus 5 plus 17. And that's going to work just as well. So this is a lot nicer because basically what we were doing before is we did a slice, then we did a reduce, which, well, 2 issues there. It's not just time complexity. It's not just the time complexity of going through that whole reduce thing over the array. I mean, that's definitely part of it, but the other thing is space complexity. So we talk a lot about time complexity. We don't usually talk as much about space complexity, but it's definitely worth considering. We don't want to overload the memory. We don't want to get too many arrays in memory if we don't have to. So in terms of space complexity, well, we don't actually really need any of these arrays. All we need are the sums. So we can just find the first k elements, find their sum, and then after we found those, just iterate through and say, add this next one, subtract that last one. Add this next one, subtract that last one. And that way we don't have any extra arrays in memory, and we don't traverse through those arrays to find the sum. So in terms of the extra space that we're adding, the space complexity in terms of the extra memory we're using, it's basically just this one extra variable sum. So that's nice. That's nice and efficient. And this might kind of remind you, at least in terms of the philosophy of what we're doing here, avoiding repetition, we're avoiding repeated calculations over an overlapping set of subproblems. Well, it sounds kind of like what we were doing with dynamic programming. So it's the same sort of philosophy, but different sort of implementation. We're trying to cut down on repetition by basically not repeating any of the overlapping parts. So Cool. Because keep in mind, like, you know, these are arrays of length 3, but they could have been arrays of length 10,000, right? So the difference between going through 10,000 elements and adding those all together versus just adding one and subtracting one, huge, huge difference. Okay, so let's go back to this over here. And basically what I want to do now is I'm just going to say, let's let sum be assigned the value of 0. So we are going to keep track of sum this time, because now we know that sum is something that's going to be changing over time. As we go through the array, sum will it'll grow and shrink. It's not going to be recalculated every single time. It's not just going to be something that lives inside the array. Okay, so input array dot length and then I plus plus. So again, we're just looping through the array as usual, like we did before, and we're just going to add the element onto the sum. Okay, so we're just saying sum plus equals input array at I. Okay, great. And then basically what I want to say is this, because we're adding the sum, like we're adding the number each time. Oh, okay. Just to sort of clarify what I'm doing here. You know how I said we want to calculate this initial sum, like the 2 plus the 5 plus the 9? Well, that's kind of what I'm doing. I'm adding them up by just putting them into the input array. What we want to know is, when do we start subtracting stuff off the left here? And basically the answer is as soon as we can, right? What we want to be doing is something like this. Sum minus equals input array at I minus k. Right? Because k is the length of the subarray, right? So we're adding on this new thing, which is kind of like on the right edge here, and we're subtracting off this thing, which was on the left edge. The thing is, that left edge might not exist, you know, like we're not going to take away an element over here or an element over here. So that's why we need to check. We need to say, like, if we don't want this being out of bounds, we're going to say, well, is I big enough? Is I greater than or equal to k? Because only under that circumstance will we actually be able to subtract off this thing to the left here. Okay, great. And then we'll say if sum is greater than max, then max is assigned the value of sum, just like we had in the last one. And let's see if this works a little better. So first of all, it's passing the sample test. It seemed to execute pretty fast, but that might just be unrelated. Let's see. Are we missing anything here? Can we fire this off? See how it works? Is it going to pass all the tests? And there we go. Yeah. So that is really a much faster algorithm. It's cutting down on the repetition. Ooh, nice. Completed the level. Awesome. Okay, it's cutting down on the repetition. It's not doing the same calculations over and over again. So basically, we kind of have two phases to what's going on here. Let's just let's get rid of some of this stuff. In fact, let's get rid of a whole bunch of this stuff. Let's go way back in time, back to when we first looked at these subarrays. So right down to here. Okay, so I just want to do a quick demonstration of how this algorithm's working. So off to the side here, we're going to have sum, and we'll have, actually maybe I'll make more space for that. I'll put it down here. So we'll say sum, and then we'll say max. Okay, and we'll see what these are equal to. And well, both of them are going to start as 0. Okay, great. And then for I, our iterator, we're basically starting at the very, very first element, or really the 0th element, right? So we're saying, okay, 2. Let's add that on to the sum. So now the sum is just going to be equal to 2. Great. And we don't have 3 elements yet, so it's just going to be 2. We're not going to do anything else. You know, we're not going to subtract anything. And we're going to say, well, I guess it will execute this line over here, which we don't necessarily want it to, but I think this is fine. It's basically saying, okay, well, is 2 greater than 0? Yeah, it is. So this will also be 2. We'll talk about why this is not going to be an issue in just a sec. And we're going to get the 5 in here. So now we have 2, we have 5. And we'll add on the 5 here. So that's going to give us 7 over here. And we'll say, well, are we ready to start subtracting off the left yet? No, we're not. Okay, we'll keep it as 7. And then that one is also going to increment up to 7. Then we'll put on 9 for this one, and we'll add that on. So this is going to become 16. And can we subtract anything off the left? Well, no, not quite yet, because remember, this is if I is greater than or equal to k, and I is the index, so 0, 1, 2. So it's not yet greater than or equal to 3. So we're not going to subtract anything off the end, which means max is just going to be 16 now. Okay, notice max is strictly growing, okay, and that's why it's not an issue, because we know none of these numbers are going to be negative, so it's not like, okay, if the maximum number was going to be the sum of these three, there's no possible way that there would be a higher maximum that's just two of these or one of these, because there are no negatives. Okay, so then finally, when k is equal to 3, we'll add on the 1 here. So we'll say, all right, this is going to be 17 now. And since this is, since I is greater than or equal to 3, now we'll cut this part off. So we'll subtract 2. So instead of 17, actually, it's going to be 15. And we'll say, well, is 15 greater than 16? No, it's not. So we'll keep max at 16. Okay, then we'll move on to the next one. We'll say 17. So we'll add on a 17 here. So 15 plus 17 is going to be 32, I think. I'm not great at math, but I think that's it. And then what's our I value here? It's 4. That is greater than or equal to 3. So we will subtract off this element over here. And then so we have to take away 5 from this. That's going to give us our 27. Is 27 bigger than 16? It is. So we get our 27 from that, which is going to be our final answer because we're at the end of the array. So basically the idea here is there are two phases to this. There's kind of the beginning phase where we're just building up the sum. So that's basically the first phase is kind of like everything up to here. Just building up the sum, getting to that first 16 value. And then the second phase is going to be everything after that, where we're just shifting from one subarray to the next. That's when we have a full set of k many elements, and then from there we're just shifting to the next one. Okay, so it's kind of two phases, but it's maybe kind of hard to see that just from here, but this is the thing that's sort of differentiating between those two phases. Okay, so that's it for that one. Did we submit? Yeah, we must have submitted. It passed the test. We have a solution over here. So yeah, that's going to be it for that one. I think, there's probably a way we could do this that does involve like slices and stuff like that, but I think this is probably the best way to do it. I can't really think of a better, more like less space complex, less time complex way of doing this, because this is just looping through the array one time. Like, it doesn't get much better than that. Okay, so we'll finish there for this one, and we'll move on to